Okay, thank you very much for the introduction. I'm Sebastian. I used to be a penetration tester and so on and so on. Now I went back to the university, and now I'm a professor at Münster University of Applied Sciences, where I teach and I do research in information security. I did 2 former talks at CCC at this very premise. One was 3 years ago, time is on my side, and one was 2 years ago. And both have a related topic because we're going to look at timing attacks in this talk as well. This talk is based on an academic paper, and I've linked it over here. If you just Google it, you will find a link to the presentation of the academic paper, if you're interested in that. Obviously, it's joint work, what I'm presenting here. So this is not solely my work that I'm presenting here, but there's a large amount of people who helped. And basically, what I was doing is the timing part of the attack, but we will see that later on. Okay, so there were lots and lots of SSL TLS bugs in the last years. So you all probably have heard of Heartbleed and Poodle and Crime and Beast and so on. So there's like a huge amount of SSL research and breaking SSL research in the last years. It's not a thing of only the last few years, but also like maybe something like 10 years ago, or more than 10 years ago. There we saw other types of attacks. So for example, the Bramley-Bonnet attack, which was a timing attack against SSL, and also Bleichenbacher's attack. It's named after Daniel Bleichenbacher. I think he's from Switzerland. And he found this attack in 1998 against a very early version of SSL. And what we are going to do today in this talk is we'll have a look whether the exact same attack still works. Some of the bugs that were discovered, like in the past, some of them were protocol level bugs, and some of them were implementation level bugs. That's an interesting distinction. So can we fix a bug just from the implementation side, or do we have to fix the protocol? Generally speaking, people refrain from fixing a crypto protocol because it requires a lot of work and it's not compatible to older versions and so on and so on. But generally speaking, when you design a crypto protocol, it will pretty much stay the same, or it has to be supported for the upcoming years. And also, depending how you design the crypto protocol, decides how much effort it is to implement the protocol. And I'm not speaking about effort in terms of lines of code, but something like how fragile is the protocol to implement. So how careful do you have to be at the implementation level? And what we're going to see today is some kind of so we have, like in 1995, when SSL was proposed, the SSL version 3 was proposed, they made some decisions that we now know are vulnerable, and they never changed it. So the SSL protocol itself is still protocol against the Bleichenbacher's attack if you don't be very careful in the implementation phase. And we're going to look at the implementation. So just a quick primer of how SSL really looks like. This is really a very short introduction. There's a new book by Ivan Ristic. He's explaining very well all the foundations of SSL and how it works and so on. So if you want to take a deep look at SSL, you might want to look at this book. I'm just going to present these parts which are relevant for this talk. So what is relevant for this talk is a TLS is some kind of a hybrid protocol. So it has some asymmetric crypto and some symmetric crypto. And generally, the symmetric crypto is used for enciphering the actual content. So when we use HTTPS, for example, the HTTP traffic itself will be encrypted with a symmetric cipher, for example, AES, and with a random session key. And this random session key will be exchanged between client and server using asymmetric crypto. So this is like the client sends a client hello, the server sends a server hello, he sends a certificate, and this certificate contains a public key. So the client receives the public key, Then he randomly chooses a session key. It's really just random, and encrypts it with a public key of the server and sends it over to the server. Now both have the same session key and can talk encrypted. When an attacker is able to somehow decipher this session key, obviously this session is broken, because the attacker can then decrypt the whole session and you don't have confidentiality anymore. This session ticket, as I was saying, is called the pre-master secret, or PMS. And yeah, as I said, the client encrypts it with the server's public key and sends it over to the server. And then the actual session key is the master secret, and this depends on the pre-master secret, right? So this is anything that you have to understand in order to follow this talk. You don't have to know more on TLS. Okay, the attack that I'm going to present here is old. It's 14 years old. It was developed by Daniel Bleichenbacher in '98, and it works like this. You have a TLS client and a TLS server, and they do a TLS handshake, and they exchange the pre-master secret, right? So the session key, for if you want. The attacker is a passive man in the middle, which means he just eavesdrops on the connection, and now has like. He has recorded the encrypted TLS handshake, and what he wants to do now is break this, like the pre-master secret, the session key. And he does that solely by requesting, by doing certain requests to the TLS server and measuring response times, for example, or analyzing error codes and anything that comes from the server. So that's our attacker scenario, and that's a very general attacker scenario. If you look at attacker scenarios, for example, for crime or beast, which were former attacks in the last few years, they have a very different attacker model, so that it only works in the HTTPS context, for example, because the attacker has to force the victim to perform many encrypted connections over the same TLS channel. Right, so he requires that. We don't need this in a Bleichenbacher attack. We just need to record the TLS handshake, and we must be able to issue requests to the server and measure something, right? And what we measure, that we're going to see later on. And this scenario means that our attack is not only applicable to HTTPS, but also to POP3S or IMAP-S. So anywhere in any context where TLS is used, our attack can be applied, potentially, depending on the implementation. Now it's not that we have broken all the ciphers that are used in TLS. That's not the case. So there's like various ways of doing the encryption and doing the handshake and so on and so on. And what we can break with our attack is this list of ciphers. Most of them are still used quite often, at least before, it changed in the last 1 or 2 years since Snowden told us what the NSA is capable of. So since then, things changed. But before that, those were, I guess, the most used ciphers everywhere. Basically, we can break all the ciphers, but none of the elliptic curve suites, because they have a different type of key exchange, and none of the Diffie-Hellman suites. So if you're using these, and you should use these because they're in generally more secure, and also at least ECC is more performant. Okay, the RSA encryption algorithm. It's really very elegant, very short, right? So when you want to encrypt something, you take your message, raise it to the power of E, and E is the public key, mod n. And when you want to decrypt M, you just take the ciphertext, raise it to the power of D, and D is the private key, modulus n, and then you get the message back. One thing that is also very important in order to understand Bleichenbacher's attack is that RSA is malleable. Malleable in German formbar means that an attacker can make predictable changes to the ciphertext without knowing the clear text. So I give you a ciphertext, or you give me a ciphertext, let's put it this way, then I can make changes to the ciphertext that have predictable effects on the clear text, even though I don't know the clear text and even though I don't know the result of my computation that I just did. Right? So you can, for example, do multiplication. So that's an important thing that we have to keep in mind when we go further. Another thing that is very important, that's I guess the second thing that is very important, we need to use some kind of padding, because the pre-master secret that we use for symmetric encryption is very short. We just need 48 bytes, so it's very short. But RSA is some kind of a block cipher. So when we have 2048-bit RSA keys, we always have to encrypt 2048 bits, right? So we have 48 bits over here, but the whole thing is like 256 bytes. So we need to use some kind of padding. And in TLS, the decision was made in 1995 to use a padding standard that is called PKCS1 in version 1.5. And always when I say PKCS1 in this talk, I mean version 1.5. There's also a version 2, which is much more secure. But always when I say, so it's like PKCS1 in version 2, right? So this is secure, but always when I say PKCS1, I mean version 1.5, okay? So just that you know. And the padding scheme is very, very easy, actually. It always has to start with 0002, at least for the encryption type. So you always have 0002. Then you have 205 bytes with non-zero padding. And this is supposed to be random, right? Whatever comes in here should be somehow a little bit random, and it must not contain zeros, because the end of the padding will be denoted by a 0 byte, and right then comes the pre-master secret, and the pre-master secret is 46 bytes of random string. Like that's the session key that we use for the symmetric encryption, and this is the part that the attacker wants to break. This is the important part. The 0301 is somehow deterministic. It means in this case that the protocol version was TLS 1.0. Right. So very easy to understand. Now, what does Bleichenbacher's attack mean? And unfortunately, I don't have enough time to go very deeply into Bleichenbacher's attack. But from a bird's eye view, it means when a service is susceptible to Bleichenbacher's attack, it allows Bleichenbacher, who is in possession of an RSA ciphertext, I call it C, to recover the plaintext of it, M0, under certain conditions. And the condition for this is that it requires an oracle. So you need to have, we call it a Bleichenbacher oracle. And this Bleichenbacher oracle does a very specific thing. It decrypts the ciphertext and responds with 1 or 0 or true or false. You can take whatever Boolean answer you want, depending on whether the decrypted message starts with 0002 or not. Right, so remember, PKCS1 in version 1.5 requires that it always starts with 0002. And when we can construct from this a Bleichenbacher oracle that tells us exactly this, so true or false, does this ciphertext start with 0002, then we can decrypt the whole ciphertext just by issuing many requests. Right, so we have to query the oracle many times. And the reason for that is, when the oracle answers with 1, the adversary knows something about the range, the possible range of the RSA clear text. And it will be in this range, and you don't have to understand exactly why this here is the case. The important part is here's a 2, and here's a 3. And we know that when the oracle tells us 1, yes, this was PKCS1 compliant, it starts with 0002, then we know that the clear text, which is just an integer, RSA works with integers, is larger than something with 2, Right? So it starts with a leading 2, and it's smaller than something with a leading 3, because otherwise it would be 0003. That's not the case. Right? So we have to issue many Oracle requests, and for each request we learn a little bit more about the clear text. Okay, this was the theory part. Now we come to the practical part. We have to talk about the strength of the Oracle. In an ideal world, we just want to have an Oracle that we can feed any ciphertext in, and it will tell us, yes, it starts with 0002 or not. In reality, this is a bit different because I told you PKCS1, the format, it starts with 0002. But it performs some more. So there's non-zero padding, and when there's non-zero padding, you should check whether there's a 0 byte in the non-zero padding, because otherwise it would be not a non-zero padding, right? So we just want to have one Oracle that tells us, yes, this starts with 0002, but what happens when we have a 0 in here? Then this might fail, or if this 0 byte here is not there, this might fail, or if this 0301 is not there, then it might also fail. So these are all additional checks that a TLS server might perform in order to find out whether the ciphertext decrypts to a PKCS1 conformant clear text. That's a problem. And the more checks we have, the worse performs the Oracle, because we could have ciphertext that decrypt to a plain text that starts with 0002, but because of the additional checks, the Oracle says, no, this was not PKCS conformant. Right. So fewer checks result in stronger Oracle, and it's better for the attacker, and the other way around. The more checks we perform, the worse is the attack. Right. Okay, so now 1998. Let's go back to 1998. Daniel Bleichenbacher came with his famous paper. What did people in the TLS consortium say? Well, they said, okay, let's just stick to PKCS1 in version 1.5 padding for compatibility reasons, right? Everything is for compatibility reasons. That's a problem, right? That's really a problem. But they made the decision, no, we just stick to the padding. We know that it's vulnerable, but let's just look whether we can find an implementation that is not vulnerable. And this is what they did. They just said, we make the requirement for the implementations that PKCS1 conformant and non-conformant messages must be treated equally. They must be indistinguishable for the attacker. So that means, for example, we had to unify all error conditions, because in the first Bleichenbacher paper, in the original Bleichenbacher paper, he exploited error messages. So the SSL implementations told the attacker specifically, no, this was invalid padding, no, this was valid padding, but it worked because of something else. It didn't work, right? So they prevented this by saying, okay, we just send one error message, and the error message just says something went wrong. So we send over a ciphertext. The server makes his thing and does all the checking. It just says, no, something went wrong, but we don't know which, right? We don't know whether the padding was correct or not, but something else could have gone wrong, something like this, right? So this is what they said: unify all error conditions. We checked for this. So we tried. So we created a lot of test cases, something like fuzzing. You might call it fuzzing. And tried to find out whether we can find Oracle in different TLS implementations. So this is an example for Java, for example, where we can provoke some error condition, where we can create a Bleichenbacher Oracle, right? And this is a very weird Oracle in a sense, right? So it will throw a very specific error, and it's called an internal error. If the clear text starts with 0002, and the clear text contains a 0 byte preceded with a non-zero byte, and somewhere in this area here. So it's only valid if it happens in this area. So it's some programming error that happened there. And because of this, we could apply the straight 14-year-old Bleichenbacher attack against this server. but we have to talk about the oracle strength, right? Oracle strength, you remember, we have a clear text that starts with 0002. That's the one that we want to have for the Bleichenbacher attack. But we do additional checks. And because of these additional checks, the oracle might still say, no, it's not valid or something like this. And here the oracle strength really depends on the bit size, on the key size of the RSA keys. So for 1024 bits, we have only 2 per mil success rate. That means let's just say for 1,000 ciphertexts that all start with 0002, we only have 2 where it really says, okay, this is a PKCS1 compliant key. And the interesting thing is the oracle strength increases with a bit size. So that means when you use 4096-bit keys, which is the most secure, this is the worst in our case because the oracle is very good. So in 3 of 4 ciphertexts that start with 0002, the oracle tells us, yes, this is PKCS1 compliant. Right? So usually people tell you that for bits, like the bigger the bit sizes, the bigger the key sizes, the more secure an encryption scheme is. And here it's just the other way around. This is often the case for side channel attacks, right? So the attack performance, we couldn't attack in reality 1000-bit keys because it just has a very low ratio. So the oracle is very bad. It required us 12 hours to recover a pre-master secret of a 2048-bit key and only 6 hours for 4096-bit keys. Okay, so here we just checked for the obvious. So we just took the 1998 paper and created a few test cases, did some fuzzing, and tried to find out whether it worked or it didn't. When you look closely at Bleichenbacher's paper from 1998, he will tell you that he created his oracle using error messages. So he just only looked at the error messages and nothing more. And there's a small sentence where he said, in theory, it could be possible to make one of these Bleichenbacher oracles over a timing side channel. And this is where we got the motivation to look, to dig a little deeper and look whether we could construct Bleichenbacher oracles just from timing information. We had some experience with timing-based Bleichenbacher attacks because we applied it against a standard called XML encryption. You will find the details in my in the talk 3 years ago, so from 28C3 was it? But just in a nutshell, I will explain you how this worked. So basically, XML encryption is a standard that allows you to cut out a part of an XML tree, encrypt it symmetrically, let's say with AES and a random key. And then you take this random key, encrypt it with the receiver's public key, and put it to the same document. And this is what you see here. So down here, you have the actual symmetrically encrypted part that you want to hide, that is where you want to guarantee the confidentiality. And over here, you have this random, the random session key, quotes, that is itself encrypted with the public key of the receiver, right? So we could attack this because all the implementations that we looked at worked as follows. Decrypt the session key in the first step, so this is this part. Return an error M if M does not comply with PKCS1, else decrypt C data. And C data is this part down here. So the whole symmetric decryption only happens if the key that was used there was PKCS1 conformant. Which is great because we can measure the timing between these two steps, right? So when we can measure this, then we have one and we can construct a Bleichenbacher oracle from this. The good thing is the attacker can influence how long it takes for the decryption to finish, because he can just put arbitrary garbage down here, megabyte-wise. So it will take hundreds of milliseconds, even seconds to decrypt. And it can be garbage. It doesn't have to be parsable at all, or something like this, because it will be parsed later on. We just want the decryption to be happening, and this is where we constructed the timing oracle, right? And here you see just this not only worked over local network, but also over the internet. So we did some measurements over the internet, and there it also worked. Right. So that was just a short excursus. Okay, so we have already experienced timing-based Bleichenbacher attacks. Bleichenbacher's attack was applied against TLS. So it's somehow natural to go back to TLS and try whether the timing-based thing works against TLS as well. Let's look at the standard, what the people said, how to prevent timing attacks against Bleichenbacher. We take the last standard of TLS in version 1.2, and they said, well, we make the processing of valid records and invalid records indistinguishable, and this is just a snippet of the standard. So they had some kind of pseudocode where they explain how the PKCS1 verification is supposed to be happening, so that no timing channel can arise. So we generate a random string R of 48 random bytes. This is a random PMS that will be generated anytime. Then we decrypt the message to recover the plaintext. And if the PKCS1 padding in the plaintext is not correct, we use R, that is the randomly generated string, as the pre-master secret, and just continue with the SSL protocol. This has the advantage that it will, server and client now have different keys. So as soon as they start talking on a symmetric level, it will fail. And what will also fail is like the HMAC authentication. So there's one part that I haven't explained yet, and that is also not necessary. Just know that it will fail later on. Somewhere in the protocol, it will later fail. And this failure does not correspond to whether it's PKCS1 conformant or not. Right? So that's a good thing, what they proposed here. This is how it's supposed to work. Here's I want to repeat this one more. So we generate a random key, a random PMSR, and in case of a PKCS1 invalid C, proceed with PMSR in the protocol. The good thing here is the random PMS will always be generated. Always, independently whether the key that was received from the client was PKCS1 conformant or not. And it provokes an error condition in the later stage. Okay, but what about TLS 1.1 and 1.0? These are older, right? So right now I have shown you the newest version of the standard. In the older standards, there was no pseudocode listed. It was just this sentence that was in here. So the best way to avoid vulnerability to this attack is to treat incorrectly formatted messages in a manner indistinguishable from correctly formatted RSA blocks. This we all understood, right? So there must not be any difference between a PKCS1 conformant ciphertext and a PKCS1 conforming ciphertext. And then they said, thus, when it receives an incorrectly formatted RSA block, a server should generate a random 48-byte value and proceed using it. And there's a difference, right? Do you see the difference? Exactly. So only when it receives an incorrectly formatted RSA block, a server should generate a random 48-byte value and proceed using it. So the 48 random bytes will only be received if the key that was coming in is not PKCS1 conforming. So that's interesting. What does it mean, right? So we have it differently. We decrypt the ciphertext, we do all these PKCS1 padding checks, and if they fail, we generate a random pre-master secret and proceed with this a random pre-master secret. And if it's not the case, if it is PKCS1 conformant, then we just proceed with this particular PMS. This has one advantage that is that makes it clear for me why they chose this approach in the former standards. It's much more efficient, or maybe not much more efficient, but more efficient. So when it comes to TLS, performance is very important. And when all of a sudden, for each and every incoming TLS handshake, you have to get a 48 byte random string, this will take some time, depending on the hardware and so on, but this might be in the milliseconds area, right? Can be a few microseconds, can be a few milliseconds, and this obviously they in former versions of the standards they thought no, it's not worth it, right? So nobody can construct a timing channel from this, and we checked, right? Let's do some timing measurements. How to perform timing channels itself is a talk, is a whole talk, right? And I always keep saying this, right? So I should do an own talk. The good thing is I did an own talk for this, right? So you can just look at the video recordings from 28C3. There I explain how to do timing measurements with a normal computer over a network, and how do you cancel out the jitter, and how can you deal with statistics, and so on and so on. How can you not prevent timing channels, right? That's the talk that came later. If you're interested in that, you can have a look at this as well. The first thing that we did is we used a TLS testing framework. It's called TIME. I don't know what the abbreviation really means, but it's credit to Christopher Meyer. He did this in his PhD thesis, and it's basically a framework for fuzzing TLS implementations. So you can generate various requests and do testing. So it's very easy and convenient to do testing for TLS. The problem is it's written in Java. That's really a problem, right? And I mean, I was expecting some trouble when it's written in Java, but so basically, I didn't know that it's that difficult to do timing measurements in Java, right? So we had to do a different approach, and here is just I tried to condense all the things that I've learned in between, like in the years of doing timing attacks over networks. What should you do when you want to do timing attacks, right? So no memory managed programming languages, no Java, no Python, no Perl, no you name it. Just use C, just use assembler, where you have a single thread does exactly what you want, and so on and so on. And there you have already you might have some issues there as well, right? But you have these memory managed programming languages as well. Choose your part of the network wisely. So there's really no issue. There's really no use of doing it over Wi-Fi or your 3G modem or whatever. Just go as near as you can to the target that you want to attack. When your attack is somewhere buried in a data center, you might want to rent hardware in the same data center, for example, right? Short paths. That's very good. Disable the power management on your measurement machine. So when you use Linux as measuring platform, you should like disable, for example, Intel SpeedStep, and there's some equivalent from AMD. It goes under a different name, but it has the same effects. There you can use the CPU frag utils. It's userland, so you can just install them and set your CPU to a fixed frequency. And there's also something which are called CPU C states or sleep states. They will just like put they will put certain cores to sleep, and in order for them to wake up, this takes some time and adds jitter to your measurements. So you can just disable this with a kernel boot parameter on Linux. What I haven't put on this list is you can also fix a process to a certain core. So you can disable certain cores, so that your measurement script only runs on this particular core. You should do this as well. Don't use fancy server hardware, because they do something that is called interrupt coalescing. And interrupt coalescing means or in the old days, when one packet arrived at your network card, it sent an interrupt to your kernel for each and every packet. And you want exactly this. The modern hardware and not only in the server hardware, but also in laptops, it's built in, and so on and so on. And there's something called interrupt coalescing. So whenever a packet comes in, the hardware will still wait for some microseconds. That's configurable, whether other packets are also coming in, so that it only sends one interrupt for many packets, right? And you don't want this, right? So use very old and cheap network interfaces, and we did this. Stop all tasks and daemons on your local machine, no UI. This should be self-explanatory. And what you also want to do, you want to, so with timing measurements, you have to repeat the same measurements over and over again in order to do statistics on it, in order to filter out the noise. And you want to skip the first few hundred measurements because usually you have some caches warming up, right? So you want to skip these. Okay. Start and endpoint for measurements is also something that that can be quite interesting. So, for example, when the request that you're sending is very big, you don't want to press the timer, right, and then start sending, and then waiting, and then come the first packets come in of the response, and then you set the timer down here. You don't want to do this. What you can do if you have the possibility is you send all the bytes of the request that you want to measure. You send all the bytes, but not the last one. So n-1, if the message is n bytes big, you send n-1. Then you start the timer. Then you send the last byte of the request. Then you wait for the receival of the nth byte of the response. Could be the first byte or something else. And then you stop the timer, and then you receive the rest of it. Okay, this is our measurement setup, and basically it's our time framework just showed in a different angle, and the timing critical part is somewhere over here. And I told you it's like time is written in Java, which is very convenient for programming, but not very good for timing measurements. And so we decided to just cut out the timing critical part, and build a module that is written in C and assembly. I didn't want to write a full-blown TLS client in C, so I looked around what was there, and then I looked at OpenSSL, right, for maybe an hour or two. Then I closed the editor and went for a walk, right? The reason for that is it's really crypto is difficult, right? And you see that crypto is very difficult when you look at the code of SSL of OpenSSL. The API is it's very hard to understand, right? And obviously there's no API for doing a timing attack on TLS in OpenSSL, right? So I wanted to reuse a part of another client, and I found this with a very tiny embedded SSL implementation called Matrix SSL. I have it written here, and we just patched this. So it's GPL'd. The code of Matrix SSL is GPL'd. It's very small, and the good thing is there's no weird API thingy happening there. You just have send and receive, for example. So you're doing operations really on a socket level, which is exactly what we want. Very clean code base, or maybe not very clean, but it's a clean code base. No complex API wrappers, and they even come with a client and a server, just as an example, right? So they ship with examples, and we just patch the client so that it does whatever we want. And what we want is we want this client to do a TLS handshake with a pre-master secret that we send him, right? And so we just created this command line tool that does a TLS handshake with a base64 encoded PMS that we just generated, and it takes the PMS, and then you have just a lock here, and then you grab over the lock and just get out the timings that you want. So you see, this is very inefficient what we coded here, but it's just research, right? So we called for each and every measurement that we did, we called a new process from Java land to the C land here, and right? So all the numbers that I'm showing to you obviously are not very good. You could probably make them faster by factor 2, I guess, but still, come on, it's research, right? So how did I do? So this is really a code that I patched in there. You have some while loop where it gets some data that it wants to send over to the server, and here you have your send syscall, and after that we just we measure the CPU ticks. If you're interested in the details here, just look my talk from 3 years ago, and then we get like the start ticks, like how many clock cycles have passed until the CPU was initialized. At this point, this is now in start, and here we have the end. Here we have just a receive, right? So it's very easy, just basic socket programming, very nice. And down here we get the end. Now we have like the start ticks and the end ticks. We just subtract them, and then we get the amount of ticks that passed and that it took for the server to just do his thing. So that was pretty much the setup. Now let's look at the code. Let's look at OpenSSL. Right. Okay, this is a real source code of OpenSSL. I think it's half a year ago or so in 1.0.1.e or I. And everything that is relevant for Bleichenbacher's attack happens within, let's say, 50 lines of code or so. So here, this line is important because there we decrypt whatever came from the client. So the client sends the encrypted PMS. This will be decrypted over here, and we have some status here that is passed as E, and this will be used over here, and then we just check in this particular if statement here whether some decryption failure happened, and if this decryption failure happened, what do? We get some pseudobytes. This heißt, we get some random bytes. We generate a random pre-master secret and generate the master key. So this is really the old way of preventing the Bleichenbacher's attack. So if and only if the pre-master secret that came in was not PKCS1 conformant, then we generate a random key and continue with that. So how does this look like when we look at the measurements? We found that it's this generation of 48 bits of random data is 1.5 microseconds. And this obviously depends on the platform that is used and so on and so on. But 1.5 microseconds, this is something that we can measure in a local network. And this is what we did. The problem that we found was OpenSSL did something very good. You don't hear this very often, right? But this is a presentation where we say they did something very good because they did a very strict PKCS1 checking. So they not only checked for does it start with 0002, they also checked does the non-zero padding not contain any 0 bytes? And is the 0 byte on the right space? And so on and so on and so on. So they did everything right. And this led to the fact that the oracle strength itself is very weak. That means even if we send a ciphertext that decrypts to a plain text starting with 0002, we still have a very low probability that the oracle will tell us it's PKCS1 valid. So therefore, we couldn't attack OpenSSL, right? So we didn't even try. We just did the math and said that it will. A successful attack will require us 4 times 10 to the power of 12 requests, and this is not practical anymore. This is not something where I would sleep very well, right? So this should be fixed, and it is fixed in the meantime, but still it's not something practical that we could do in our lab. Let's look at the third channel, and this time again, we look at the Java implementation of TLS. So these were the same guys that had this, like the different error message, right, 20 slides ago or so. And when you look at this, so we have some master secret here, and we want to generate the master secret. We get some information and try to generate the master secret over here. And what you see here is there's a lot of exception handling, right? So what they did here is actually textbook Java implementation. This is how I teach programming beginners how to do object-oriented coding, right? The problem is this is not a really good idea to do this in a timing critical sense, right? So it basically means you don't see this at the code here. I only show this to show you that there's a lot of exception handling and catching and throwing new exceptions and so on and so on. It led to the fact that we could exploit this. So we could execute a timing-based Bleichenbacher attack against JSSE. The Oracle strength was very strong, so they do very few checks. So when you send over a ciphertext and it decrypts to a plain text starting with 0002, we have a 60% chance that the Oracle will tell us, yes, this is a PKSys1 conformant. And it means that we could break one single TLS handshake within just about 18,000 requests and 20 hours, which is pretty good. The fourth channel, and maybe the most critical channel, was when we looked at some hardware TLS accelerators, concretely at those from the company Cavium. So whenever you buy a big appliance for big money that does the SSL termination for you, so let's assume you have a lot of requests that you have to process, and you have a lot of application servers and a load balancer, then usually the servers behind the load balancer, they don't terminate a TLS. It makes some box before that does it. And if you buy such a box, it often contains a hardware acceleration for TLS, or at least for the underlying crypto primitives, such as AES and RSA and things like that. So that the expensive part of the crypto operations is performed on separate hardware. This comes in various flavors. For servers, you can also buy this and plug it in via PCI. Then you need a driver and so on and so on. So yeah, and it's then relevant when you have like a big installation and you have to deal with many thousands of incoming TLS handshakes and connections and so on and so on. Then you need an appliance like this. So we analyzed this as well. And concretely, we looked at the products F5 Big IP and IBM Data Power. So we didn't have the actual card. We just used products or measured against products that have these cards installed. And this is very interesting, a very interesting behavior, what we found here. So for example, it doesn't verify whether the clear text begins with 0002. It just verifies that it starts with something 02, which is weird. But one possible explanation, I mean, we have talked to the developers, but we didn't ask them about this. But I guess it's again something performance, right? So they didn't care about the first byte. They only cared about the second byte. This brought us a little trouble because the Bleichenbacher's algorithm, the textbook algorithm, requires that something starts with 0002. So we had to adapt this Bleichenbacher's algorithm so that it also works with something or 02, which makes the Oracle somewhat weaker, but we could still apply the attack. And we required 4 million queries, which is a lot, but it took 41 hours, right, to decipher a TLS handshake of one single TLS handshake. Okay, let's just make a summary. So the first thing, that this is not something new, but not many people have achieved this so far. Timing attacks against single-digit microsecond delays in TCP connections are practical. So there are other papers who did this against DTLS, for example. That is a datagram-based service, so like UDP, for example. You send something and something comes back. It's a bit more involved when you want to do the same over TCP connections, but we found that it still works, which is good. a bad design, and I should have quotes here in bad design in cryptographic protocols, may taunt you for decades to come. When in 1995 they make the decision that RSA and PKCS1 in version 1.5 is a good idea, they brought a lot of trouble. Right? So they didn't know that this can be exploited that easily during that time. They had to wait until 1998 and until Bleichenbacher showed this. But the problem is we have been living with a protocol that is known to be broken for 14 years. And now I hope it makes sense when you remember the thing that I said on one of my first slides, where I said protocol decisions, it can be very fragile, right? So everything that you have seen here, like the implementation of TLS in this specific part, is very, very fragile, and you have to be very, very careful to do exactly the right thing. And then also, what is taunting us is Magnan encrypt. So obviously, it's not possible in the TLS protocol to just send them random ciphertext over there and expect the server to do something useful with it, right? Also, you have a thing that guarantees your authenticity. So you have a message authentication code, and this is where it will fail anytime. But the problem here is you have Magnan encrypt. That means the message authentication code is appended to the clear text and then encrypted. Which sorry? Yeah, so, thank you very much. So the problem here obviously is, in order to check the message authentication code, you have to decrypt the ciphertext beforehand. So there's a lot of code running before you can actually check whether this is a valid message, right? So this is bad. What you want to do is encrypt then MAC. So you make you encrypt your clear text, you have a ciphertext, and then you do your message authentication code on this. And then the message authentication code is appended to the ciphertext and sent over to the receiver. Yeah, implementing TLS is a minefield, and this may explain why everyone keeps complaining on the code quality of OpenSSL, for example, right? So look at the Java code; it looks much better, right? JSSE is really nicely object-oriented and everything, but it can also be broken, and it's broken in more ways, I think, than OpenSSL was. Okay, guys, thank you very much. I'll be around at until the 30s, so if you want to talk to me, just do it. I'm happy. Thank you very much.
Thank you very much. Now it's a little bit time for questions. I know that there's one question in the internet, and they were discussing this question for some time now. So even if they managed to answer it, maybe it's interesting for everybody else. So I think we should start with this.
Yes, there was some discussion going on about how hard is it to prevent this kind of attack, and is it possible to do some random sleep in the code to prevent the attacks?
Okay. So the question was, is it possible to fix it with just a random delay, right? No, that's really a bad idea. I've spoken this at length at my 29C3 talk, so you can have a look at that. The reason for that is you will decrease the performance and the attack will still be possible. So this is not a good idea. You should just fix it in the code. It's possible, and at least for open source code, you have like the source code.
So there are some more questions, and I ask everybody who is leaving to be a little bit more silent, so that the people who want to get the answers can hear them. Thank you.
Hannes Czefinik. I specifically am interested in hearing about how to mitigate these problems in the future. You were referring to sort of the guys who worked on TLS standardization, they did make some mistake. But on the other hand, the work is taking place in an open forum, so there's a possibility for people to engage, and that would obviously help. But what are other ways to deal with those issues in the future?
So the problem is really, so TLS was in 1995. XML encryption did exactly the same errors in somewhere in the 2000s when it was long known that this is vulnerable. There's a new thing that is called JSON Web Encryption, JOSI. They did the same errors over and over again. So we just see the same errors in protocol design over and over again. And they always argue that you need to support these broken ciphers for compatibility reasons. So they have the problem. If they don't support the broken ciphers, nobody will use their standard. That's the problem. Which is a pity. Sorry.
The last question from there.
In your presentation, you talked a lot about PKCS 1.5. Did you have a look at the PSS signature scheme as well? And can you tell us if this is somehow affected by this problem as well?
Like the signature theme that is PKCS 1 in version 1.5?
I don't think this is part of 1.5. The question is if the PSS signature scheme has a similar problem.
Not that I know of.
Okay,
not
thank
that
you.
I know of.
So